Hi, and welcome to According to Pete. It is cold in Colorado, man. Today, what are we going to talk about? The same thing we talked about last time, some PCB layout. There were some questions in the comment section posted by Superflyer. I don't know who Superflyer is. I have no affiliation with Superflyer. But asked some good questions, and I thought it would be a good idea to address those sort of like soon after the last video, so people can sort of see the twin effect of two videos. Not one, but two videos on PCB layout. So that's what we're going to talk about. Superflyer coming to you! So the first thing that Superflyer asks is about through holes via placement, optimization, and minimization on a two-layer board. The Eagle router loves to shuffle through holes between high current SOT23 MOSFETs. The first thing I will say is don't get victimized by a rogue auto router, man. Don't let it, you know. If you want good results, you got to do the work yourself. I guess some auto routers can be optimized to better reflect what you're looking for, but you know what? You're just going to save a bunch more or a bunch of time by doing the layout yourself manually. As far as the rules of placement for through-hole components and the associated vias, same sort of rules apply as with what we talked about with surface mount, which is to say that if you've got components that are physically, or if they're close in a schematic, then they should be physically close to each other on your PCB layout, okay? Now, for example, you know, you got your op amp here, and if there's a dual op amp, that's going to be an output. These two are going to be inputs. You're going to have some da-da-da-da. Now, if you got to start using through-hole resistors on this, what you would do is, you know, so it's going to be kind of like that, and it's going to be goofy. And, oh my gosh! So your loops are going to be bigger, right? And these are the things, your traces back to high impedance pins. That's something I was a little bit stringent on in the last show. Your traces are going to be longer. There's no getting around that. But that's not the end of the world. Remember that I also said that the success of your circuit design is, at least to a very large degree, probabilistic, okay? So the shorter, the more compact your circuit design, the shorter your traces, the more likely it's all going to work as intended initially in the end. Now, in terms of component types, if you're using through holes, caps have gotten pretty good about tightening up, right? Because it's only a couple of plates, you know, on a pin. And these are usually spaced like 0.1 inch apart, or in some cases even tighter. So that's not that bad, right? That's almost an 0603, 0805 package width. You can deal with that. These guys, same thing. The components have gotten smaller. You know, it used to be that quarter watt resistors were the norm. Now you can get 6th watt or 8th watt. They're really tight. But one little trick that you can do with these guys is you can actually physically stand them up. And when I say that, to give you an idea, so you got one via here, and you put the other one right here. So this will be like, you know, 0.1 inch spacing, and then you take your resistor and you got one pin here, and you just stand this guy up, and you got one pin there. You got so are your traces actually shorter? Well, it's probably a wash in the end, but the physical space that it occupies on the PCB is not as big as it would have been otherwise. The question arises, well, why do we use, since we have surface mount and we can make this a nice tight little package, why do we bother with these at all? There are some reasons why you might have to use a through-hole component. For example, power considerations, like a large regulator, like a TO220 package. Although you can get big sizes that will also be surface mount and take up not very much space. But there's still a lot of pieces that are only made in through-hole design, so you can get a good heat sink on them. So you may still be constrained to use some through-hole stuff. In terms of resistors, again, if it's not a power consideration, you can go to a surface mount part. And, you know, I and we, the guys around here, and girls, we do like to use predominantly 0603 packages. They're just enough small that they make a nice tight design, and just enough big that you can work with them, so they're not completely unfriendly. But I'm starting to get older, right? Those tiny parts are getting harder and harder to deal with every day. So you can go to potentially an 0805 or 1206 or 1210, And those components are, you know, they're pretty big. I mean, if this is our point of reference, you know, 8-pin dip, you know, that might be a 1206, you know? So compare, I don't know how close I am. Oftentimes, if you can go to a surface mount layout, you're going to save board space, you're going to save your trace lengths. So stick with that as long as you can. The next question has to do with via size, right? The holes that go through top to bottom layer, and how much current carrying ability they have. I went looking for this information because I didn't know off the top of my head, and I found a couple of different sources. The first source I actually found on Screaming Circuits, a website called Screaming Circuits, posted by an anonymous person who referred to themselves as AC. And at the bottom, after they posted all these numbers, they said, gosh, I really hope somebody got helped by this. I got helped, AC. I got helped. Now, what AC said was he compared, or she, I don't know, she compared current or drill hit size against how much current you can expect it to carry based on a 1 mil copper thickness, okay? Now, I don't know where AC's numbers came from. I don't know how accurate these are. But you can see, and he goes on from 10 mil to like 60 mil, and I've only got down to 40. So according to AC, a 10 mil drill at 1 mil copper thickness will carry 1.12 amps of current. That's a lot, man. Reference, remember also that 1 ounce copper weight is about 1.37 mils copper thickness. So you can generally expect better performance, if we are to believe these numbers, better performance in this in your own 1 ounce copper design. Now, because I don't know how accurate these numbers are, I went looking for another source. Hopefully one that has some kind of credibility that I can depend on. Didn't find one immediately. But I found a rule of thumb that says, or 3 times the current capability of a similar size trace. Now, admittedly, these numbers, and that's a rule of thumb, right? So I don't know how accurate this is. So I have to temper it with what I know about a via against what I know about a trace. If this is a cross-section of a PCB, right, and that's our drill, you know, a via is going to have a bunch of metal here, it's going to have the inside coated there, and it's going to have a bunch of metal there. And if you've got like a 10 mil trace or something going to that via, this is not going to be the weak link in your signal, right? I would worry more about like parasitics that are generated in this shape, right? Because this thing is going to choose, the current through this is going to choose like the path of least resistance. So you'll probably get some current on the inside wall going like that, and on the other side too. And then you've got kind of a funky capacitor, maybe some inductance. But you know what? This never ends up being an issue for anyone that I've ever heard. But then I've never done any really high-speed design. But getting back to the actual question, how much current can you expect any given via to carry? These numbers, the 3x the size of a trace, and some of the higher numbers in AC, not alternating current, I don't think. Thanks again, AC. They start to line up more when you get to the higher drill hits for a via. So I kind of believe the rule of thumb pretty well. Although if I'm laying out a high current trace, I'm going to probably use a few small vias rather than one large via because it tends to line up a little better with the 3x rule. One last point that I will make is that in our own designs, SparkFun designs, we rarely go below a 20 mil drill hit for a via. We do sometimes when a design calls for it, but we usually like to have a lot of forgiveness in those sorts of things. So we like to have big vias. We like to make sure it's a low impedance. We like to make sure we've got really good continuity. What the heck? Okay, so the next bit that Superflyer asks is non-VCC ground copper pore areas. So we talked before in the last show about using a big copper pour for a ground plane or a VCC plane. And a Superflyer asks, would you do that for anything else? Or what about doing that for anything else? And my only experience with doing planes that are not either directly VCC or ground is when you have two separate grounds on a part that has both a digital section and an analog section. So you've got an analog ground plane, you've got a digital ground plane. So let's say, for example, you've got a part that has both an analog section and a digital section. And what they will do oftentimes is they will give you like analog ground pins versus a digital ground pin. And hopefully, if they've designed the chip really well, they will have those sections separated internal to the chip. And I've had to do this on a few analog devices parts. They're big on doing that. They got a digital front end to something that's got an analog input. And so what they say is, okay, we want you to run a ground plane that looks like this, and picture this running under the part, right? And they may specify this or they may not. So oftentimes what you want to do is you want to find the sections, and again, it's if they've done the design of the chip well, these sections will be different internal to the part. And so the pins will reflect that, right? So you've got all your digital pins like right over here. So what you would do is like maybe this one's the ground. So I might not put my ground plane there, or my analog plane. I will put it like, right up underneath those parts. So my analog plane is taking up as much space underneath the chip as it can. And then what they will say is connect the ground plane in only one place, connect the digital and analog ground. So you will have like two different ground planes that run sort of like this. And this is empty space in the copper, okay? And then what you do is you make like one connection between the two copper planes on the bottom side, okay? And the reason they do this is to keep noise out of the analog section, right? Digital communication and digital function in general, and I've explained this in previous videos, I know I must have, right, when you're running a square wave, that edge, right, everybody think back to college days, if you've been to college, the edge has a lot of harmonics. Well, that's a really terrible edge. So the sharper that edge is, the more high-frequency harmonics are in that thing, and that's noise, right? So you want to keep that kind of junk out of your analog section. This is as I said, this is my only experience with having separate planes. Now, would you have a plane for any other signal in your circuit? I'm trying to think of anything I may have done that required that, and I can't come up with anything. So I invite the viewers to comment below on if there's another application for having. I mean, you can do it, right? You can, and it's not necessarily going to impact your circuit dramatically, but what is a good reason to do it? And I'm not talking about art. I want to be artistic with my layout and make all kinds of fancy shapes and stuff. Well, it'll probably have a negative impact of some kind, but I'm trying to find something that has a positive impact. Why would you do this with anything but a separate ground or a VCC? I'd love to know. So the next thing that Superflyer asks is wisdom/fallacy of routing heavy ground VCC paths around edge of board. And my question to you or anyone, why would you do this? Now, admittedly, I do not have a textbook rule that says never do this. Do you really picture me as being somebody who follows textbooks all that much? No, I'm really not. But let's investigate it. Let's think about it critically for a moment, if that's possible for me. And let's say, for example, you've got, your power's there, and you want to run a big old trace of power around the side, and maybe you got another connector over here, right? And you're kind of daisy chaining these things, and that's not necessarily bent. I don't really care. Now, I can see a reason for like a daisy chain design to maybe do something like this. Is it better to have it around the outside edge than go straight through the middle? I might resort to doing something like this in order to keep a solid ground plane under the circuit, because if I take this right down the middle, I'm going to split the ground plane, and that's going to be kind of goofy. So there's one reason why you may do something like this. Now, if you're not daisy chaining, and you're like, you know, feeding circuit sections like this, that's kind of goofy. I would not do this, and the reason is because I prefer to have a star configuration. Although you could argue that there's so much copper here that it's virtually a star configuration, but it's not. My other gut reaction to this is anytime you do something like this, you're basically making an antenna, right? It's either transmitting or receiving. So you can really expect to have some difficulty when you're doing that sort of thing. If you're not daisy chaining your design, I would not do anything like this. I would do it more the way I suggested the last time, which is, you know, a centralized power and a star configuration for feeding your power. Most of the time, if I'm making big traces on a PCB, I keep them as short and to the point as possible. Big current paths, I want to get off the PCB as quickly as I can, right? I trust a big, thick gauge piece of wire to carry more current than a big piece of wide copper. I want a wire. I don't want that. Final question, sensible QA or test points. How? If I'm testing a board, be it prototype or production, the things I'm going to want to know the most are going to be, you want like power in, like you're going to have some power in, and then you're going to have a regulator. Since when is there a wire between a decoupling cap, Pete? Really? And then ground. So you're going to want to test like, you know, this will be your VCC or your first VCC. And you may have several different regulated voltages, you know. And you're going to want to know all of those. You're going to want to know, first of all, you want to know V in. So you're going to want a test point there. And you're going to want to know what, you know, your VCC is. You want a test point there. You want a test point here on this other regulated voltage. All your regulated voltages, you're going to want to know right up front to tell you what your circuit is doing, first and foremost. Because, of course, if it's not working, what's the very first thing you look for? You look for power. You're also going to want to know about how much current you're drawing, okay? So your voltage in, you're definitely going to want to interrupt this on a test fixture of some kind, and you're going to want to put a meter to see how much current you're drawing, right? Because the first time you power it up, if it's drawing more or less current than you expect, you know you got a problem, okay? Now after voltage in and all your regulated voltages and your current, test points are going to become a little more esoteric, perhaps, and this will be dependent on the circuit that you're designing, right? So if you're designing a predominantly digital circuit, you may want to read something like a reset pin on a micro, or various other pieces, or you may want to keep an eye on when a certain digital part is coming up, right? When it's powering up and when it's active, so there might be a couple of pins on that. If you're designing an analog circuit, and you know, I love op amps and I love my transistors, you're going to want to know about you know, specific voltages according to that. You might want to know the output state of an op amp, because that will either tell you if the op amp's bad, or if something, you know, in the previous stage is bad, or your biasing resistors are not well adhered to the board. There's two different kinds of testing that you might be interested in. Number one is testing a prototype, where you have to look at various points of the circuit to make sure they're working the first time. And then there is testing for production, which is a different thing. By the time you're testing in a production setting, you already know what the circuit is supposed to be doing. So you don't necessarily care about you know, all of the bias voltages in places. You might be monitoring something close to a mechanical part. And I'll tell you something, In all production parts, you are going to have many more mechanical failures than you will have electronic failures. Electronic parts fail, but not as regularly as mechanical ones. Pots, power jacks, screw terminals. Man, I hate screw terminals. Anything that has anything to do with a mechanical force, twisting, pushing, any of it, that stuff goes bad sooner than electronic stuff does. So in a production setting, you're going to want to be putting, for example, I've got an antenna that is it's like an active antenna that's got an LNA in it. For example, it's got a GPS antenna, just for example. You might want to measure on a board that you've designed that the output at your SMA or UFL connector is actually at the power that it's supposed to be, okay? And you might want to put a load resistor in your test apparatus to make sure that it's going to source as much current as you need it to be. So that's what I mean by, some of these things are going to become esoteric. And it's going to depend on whether or not you're testing a prototype or you're testing something in production. And, the reasoning behind those test points is going to be different. In general, you're going to want to know your V in, all your regulated voltages, and the current in. That's going to give you the most information about how your circuit is doing. If it doesn't work after that, it's really dependent on what your circuit looks like and what sort of design you've tried to accomplish. That's everything. Thanks again, Superflyer, for all of your super cool questions. Anybody, if you see anything that I've missed, or you think of anything that I should have explained better, or I said something silly, please say so in the comments so we can start a dialogue and see where it goes. Thanks for watching. Until next time, you can check us out at SFE_engineering on Twitter. Please do. And that's it. I'll see you next month. Commence faking. 3, 2, 1, fake! That's going at the end of the video.